I'm Stephen Foskett, and this is Tech Field Day. The video you're about to see brings together a panel of a dozen delegates from around the world who focus on enterprise technology to talk and learn about new technology products from companies like DriveScale. If you'd like to learn more about this, you can go to techfieldday.com. And if you like this video, you can see a lot more at youtube.com/techfieldday.
Morning, everyone. So I'm Tom Lyon, Chief Scientist. That means I don't do much work, I just talk about stuff. So if you look at the kind of history of the data center, and five to 10 years ago, people thought things had settled down pretty well. Everything was going to be virtualized. You had relatively homogeneous pools of compute, and then the storage was off in the back end somewhere. And that was really dominant model. But there were always a few outlier systems, like your Oracle database. You didn't really want to virtualize that. And so, of course, that's still a huge thing. But that's not what we're here to talk about. We're here to talk about scale-out, where it's a whole new level of economic efficiency. It's a whole new level of size of application. It's the data avalanche, et cetera. Big data just changes all the economics of these things. Traditional storage systems have not been able to keep up at all with the data onslaught, so we're seeing a huge profusion of new types of software-defined storage, scale-out storage, whatever. So, and it turns out storage systems have all evolved to be just servers with hard drives, right? There's pretty much whatever hardware differentiation used to be there is gone. So the key, and then a key part of what we define as scale-out is the ability for the software to tolerate hardware failure. And that's something that the HPC guys don't quite have. If one of your 1,000 processors dies during your weather combination, you sort of have to restart from a checkpoint. And then another key thing is there's so much data that data locality has become very useful. And so this is the key innovation behind Hadoop, is being able to move compute to the data on whatever storage servers there are. And this is a critical piece of the Hadoop architecture, locality, and it's something that most other, lots of people complain about Hadoop storage in one way or the other, but most of the traditional storage systems can't supply the kind of locality that Hadoop needs to be able to read from thousands of hard drives at once to do analytics. And so you'll hear about how we can provide that locality. So I'm sure you've seen all the data centers, racks and racks and racks of commodity servers. This is the new normal. Not much redundancy in any one server. Top-of-rack Ethernet switches. Maybe you'll have 2 switches for redundancy, maybe not. Very complex cabling and direct attached storage. So the interesting here is, what happened to blade servers? Why didn't they take over the world? Because they have such better reliability characteristics, reduced cabling, it keeps you from knocking stuff out, and better cooling, and all kinds of good things about blade servers. And we're very proud of what we did at Cisco. But the trouble is, blade servers were built to handle fragile software. Scale-out software is not fragile anymore. So who cares how reliable the individual server is? So the whole software stack is changing to where the things you really valued back in the blade server era just aren't needed anymore.
You're saying it's matured enough to the point where it isn't fragile? Because that's an argument I hear about against a lot of this, is that the complexity that is added introduces fragility, and the software is constantly iterating. So it's always challenging to keep this stuff running. It's
far from mature. I mean, but this is a nascent market. It's one that's it's not taken over the world yet, but it's getting there. In the same way that you want to take your first few releases of VMware Workstation and run your critical apps on them, right? And you run big apps with scale-out. You eat servers by the dozens, so there's no point virtualizing the server. And in fact, they're so I/O intensive that there's a lot of overhead still for I/O with virtualization. Very tolerant to the hardware hiccups and failures. They're very much network aware and bare metal aware. most traditional apps living in a POSIX API world, they know nothing about a network. The scale-out apps are specifically doing socket calls to share stuff with their other instances. And then things like Hadoop, HDFS are specifically aware of hard drive characteristics. The reason a Hadoop block size is 128 meg to up to a gig is to amortize the seat cost on hard drives while you're doing stuff. So things have changed a lot, and the new apps, they don't need no stinking stuff. SANs, NAS, virtual machines, vMotion. I mean, how cool was vMotion when that came out? And with scale-out, you say, I'll start up a new instance and then kill the other guy. Fiber channel, software-defined networking. It's all about optimizing your layer 2 networks. Yeah. Scale-out doesn't do anything with layer 2. So there's a whole different world here. Typically today, scale-out's built with these 2U servers, which I call the minivan of computing. They're very versatile. One server will do anything that one server will do, but they're not really optimized towards anything in particular. And so you don't really want a fleet full of minivans when what you need is either taxis or semi-trucks or whatever. Race cars. Motorcycles. And so the trouble with that direct attached storage, and I should mention the other key thing about direct attached storage is just the raw price, right? So SANs are like multiple dollars per gigabyte usually. NAS maybe down around $1 a gigabyte. Buy the hard drive straight from Seagate, 2.5 cents a gigabyte. Huge differences in the economics, and when you buy it through a server vendor, it's still a whole lot cheaper than buying it from a storage vendor. But again, when you buy it all in one box, there's no flexibility. So you need more CPU, you add disks with it. You need more disks, you add CPU with it. So the more you grow, the more obvious it is that things are out of kilter. Hadoop in particular really likes to see the drives spread across all of the compute nodes so that they're all kind of homogeneous looking. Otherwise, you need intelligence to say, well, this app needs to run on a compute intensive node versus a storage intensive node. And that intelligence doesn't reside anywhere, especially with the user. So scale-out infrastructure is very inflexible. So what do you do to bring back some of the flexibility that you could get with NAS and SAN in a way that's still appropriate for scale-out applications? So we're talking a lot about Hadoop. So why Hadoop? Intel invested about $700 million in Cloudera. And this is the real reason they see Hadoop being the most important hardware consuming application in the data center. And HDFS in particular is for all its warts, it's a very sticky kind of file system. It's the data lake. And people just dump and dump and dump stuff, and it grows and grows and grows. And we're at the point now where big data is defined as what happens when it's too expensive to figure out what to delete. And so this is very good news for us in the hard drive industry. Our Hadoop definition is anything that depends on HDFS. So that includes Spark, Flink, Pig, Hive, any of the other 50 frameworks. So we don't care which of those you use. So, and of course, Hadoop, people have very large clusters where they're very much aware of this imbalance problem, and things are still growing very quickly. So that's the fundamental business focus of the company. So why a rack scale architecture? And that's kind of what we're promoting with our architecture, is how do you optimize the servers in a way that spans more than one box? And there's different techniques to do this. You can aggregate by putting lots of stuff in one box. We see that a lot with the the denser servers now, 4 servers in a 2U box or whatever. And that reduces power, cooling, cabling problems. The other technique is disaggregation, right? So take apart the servers from the hard drives, and now you can optimize the chassis, optimize the life cycles, optimize the delivery of the components separately. And that's really what we're all about. So it's we're refactoring the hardware the way people refactor software all the time. So different reasons to do the rack scale optimization. One is, the sharing I mentioned. HP, one of their Apollo systems, is all about water cooling for the very highest density compute systems. So that's a different kind of rack scale architecture. We're more interested in balancing the ratios between CPUs and disks and SSDs, which also enables different lifecycle management of those components. And in the future, we're going to see disaggregated accelerators like GPUs. 100 gigabit Ethernet is already about the same speed as a 16-lane PCI Express bus. So it should be entirely feasible to move GPUs off. There's a lot of FPGA accelerators coming around in the data center. So all these things can become subject to disaggregation. So you worry about how do you build a rack instead of how do you just build one box. When you do a rack scale thing, the fabric is really the essential question. Are you going to build on PCI Express, InfiniBand, Ethernet? Do you use RDMA? So different comments on the different fabrics. So PCI Express, it's great for what it does, but it's not much good at running out of a box. It's not symmetric, so you can't go server to server. It's fragile drivers, right? So if you break a cable that's got PCI Express running on it, the system goes nutso. InfiniBand used to be king of the hill for this kind of thing, but now Ethernet can do pretty much everything InfiniBand does. Top 500 just came out this week. 13% of the systems on it use InfiniBand. So it's not that many. So Ethernet, 10 gig is kind of the default right now, but 100 gig is already available. All a matter of cost. You can get less than 10 microsecond round trip latency through one switch with almost any protocol, including TCP. And then the question is, do you use RDMA? And I personally hate RDMA, but a lot of people love it. The trouble is there's several flavors: Rocky version 2, iWarp. There's not very good support for RDMA on the server side because there's no pure software implementations. So it's a step function you have to make to decide to use RDMA.
So based on the slide, I can assume that you're using Ethernet?
Yes, so vanilla Ethernet is yeah. I used to be an ATM guy, so I got run over by Ethernet once already.
Don't need it again.
Yeah. ATM was the kind of ATM that you only put money into. So, and then we're emphasizing the architecture part of what we do. We're not interested in selling the appliance, although our customers and integrators may do that. What we want to do is to provide the architecture. Appliances, they're very easy to buy, and there's always going to be a part of the market where they're more concerned about how easy it is to buy something rather than how efficient it is. But as you scale bigger and bigger, you worry more and more about efficiency. And architecture is really about the choice and evolution and how to cook your food. So it's really fast food versus a good cookbook. And somehow the Big Macs I've had never look that good. So we call ourselves Smarter Data Center Infrastructure for Scale-Out. We're all about managing the scale-out hardware. We have complete visibility into the topology of both Ethernet and SAS in a rack. So we understand exactly how much bandwidth is where, and what the capabilities are for multipathing and all that good stuff. We can gather this information at scale, so we can tell you, hey, out of 100 servers, you have 3 that aren't duly connected. There's probably something wrong. The core of the product is then providing configuration flexibility. And this is the first thing to get over is when I say cluster, I'm talking a logical entity, not physical. Whereas most people today think cluster is like, oh yeah, this stack of hardware or that stack of hardware. So today we're saying cluster silos the same way we saw server silos 20 years ago before SANs. And that's bad. And typically the reason you have these silos is because every cluster demands a slightly different server configuration. So by having configuration flexibility, we can start to have a single pool of hardware to carve logical clusters out of.
You're using Ethernet, obviously, between nodes, SAS inside of a node. Are you doing any form of RAID inside of that, or is all the intelligence built into the software?
It's all for the software. So, and then we'll have cloud-based services for central intelligence gathering. So here we give people the tools and levers to reconfigure things. Here we'll give people advice on how to do it. So we'll be able to understand that over time that kind of what the best practices are from different customers and feed that back to the other customers.
So what kind of information are you sending back dial home-wise? And do you store that for a long period of time so can customers go and look at their statistics and things like that via your portal?
That's the intent. We don't have much there today. And the first real service we have is just backing up the configuration of everything to the cloud. But we have the ability to ship log files up. It's all based on whether the customer wants to do that as well.
But your future intent is to show common configuration scenarios based on your larger install base?
Yeah, and to be able to kind of do what ifs. You know, what if I had a different ratio of hard drives and CPUs? It's like, oh, that's been done over here, and here's their relative efficiency for certain apps, and it's just gathering all this stuff and applying analytics and machine learning to it. So that's a much longer term thing, and there will no doubt be pieces we steal from other open source projects and things like that.
And going back in the other direction, do you have any specific access over customers' equipment? So, for example, to do remote patching or troubleshooting, those kind of things?
We don't have it built into our product, but if they give us VPN access to their network, then we can get into our stuff.
Right.
So here's the picture about what we do. Again, typical scale-out rack, bunch of identical servers, each with their hard drives. What we want people to do is build racks now where you use server FRUs that are whatever you want. It could be completely diskless, could have disks, might be blade servers, could be micro servers, it's whatever you feel is appropriate. And all the hard drives are factored out into industry standard JBODs. And these are dumb JBODs. There's no processors down here. So it's kind of like, and again, part of the reason people do this is because it's pointless wasting processors on storage these days. They're much too powerful for that. So this is hyper-converged and Hadoop and all those things. So the same thing here, you don't waste the processor just on storage. We provide our DriveScale adapter, the box on the table here, which is essentially a dumb Ethernet to SAS bridge. So it essentially gives a iSCSI target to each of the hard drives, so they can be independently assigned to any of the servers. Now, many of you should have shuddered when I said iSCSI, if you've ever actually tried to manage it. But because we control both ends of the connection, the user never sees iSCSI.
It's your problem.
It's totally our problem. We've found bugs in the Linux iSCSI. We work around them. We also control multipathing. Typically, you'll see with one of our boxes, there's 4 controllers. There can be 4 paths between any server and the adapter, and then 2 paths between any adapter and the JBODs. Again, all that multipathing is set up and handled transparently. And then we have another layer of load balancing software to make sure that we effectively use the bandwidth coming out of the servers. So if you have more we typically recommend 2 10-gig links at least. So depending on how you set those up, it can be easier or harder to actually get all the bandwidth out of them.
So just so I can kind of maybe explain this to myself, the customer is providing the CPUs in whatever manner they want.
Right.
The customer is providing the disks in essentially whatever manner they want.
Yeah, in JBODs, but yeah, they have a broad choice.
But you're providing that appliance basically as the connection between the two of them.
Right. So it's best to think of the appliance as a switch extender.
Right.
It's a way to get SAS onto your Ethernet switch. Now, the Ethernet switch is of critical importance because it's providing the bandwidth to make all this happen. Okay, our things are just a bump in the wire. The bandwidth comes from here. And the reason there's so much bandwidth is because almost everybody has a choke point coming out of the rack of 4-to-1 over provision. So that means there's, what is it, 4/5 of your bandwidth left over that can't go out of the rack, so it's usable in the rack. So that's a huge point that a lot of people don't get. And then people worry about, oh, what's going to be the performance? You're going over the network. And I say, no, we're not going over the network. We're going over a switch. So a non-blocking connection. Very, very predictable performance.
So that's a unit of storage. If I want to go bigger, I need more, I build another rack that is an independently functioning unit.
Right. So it's rack by rack. And the racks don't have to be exactly the same shape. They can interoperate with racks that don't use our stuff at all. And you can have the same Hadoop cluster striped across them.
Like, what's the core value prop to this? I mean,
Okay.
what do you solve?
Funny you should ask.
Okay.
So the core value prop in my mind is the destruction of the silos. So instead of having all these different physical hardware silos for different types of clusters, you got your Hadoop, you have HBase, which is Hadoop, but a little different, so it had to have a different hardware config. You got NoSQL, you got object storage, you got Ceph, you got whatever. They're all going to be separate little hardware silos of clusters, and there's really no need for that. You can standardize on some kind of server through, and then assign your storage capability to those servers as you like. So here we show 3 different clusters, very different needs for hard drives per node on each cluster, and the boundaries are totally movable. Servers can be moved much easier than drives because they don't have any state per se, right? And so it's very easy in our software to move the servers to a different cluster. Standard server provisioning tools can re-image the server if they have disks internally, and that can be done in 5 or 10 minutes these days. And then you're off to the races with you reassign the drives, and you're off with a new kind of cluster. You can create a cluster out of thin air by taking away resources from underutilized resources. And so what we can do for your hardware, for your data center as a whole, is what VMware can do for a server. Slice and dice it, change the size of different nodes, and make it possible to create new things without a physical hardware provisioning process.
So one of the biggest values, as you'll see when I get into the use cases, is the life cycle management. So you can upgrade your processors and just leave your disks in place. And right now, if you want to upgrade the processors on a traditional rack, you have to throw all your disks away as well. And that makes it a very much more expensive and time-consuming effort as opposed to just throwing in a bunch of new servers and the disks reconnect up and away you go.
Okay, so you're saying the main value is disaggregating the hard drives from the processors that we're typically doing in a scale out. So you're providing the scale out inside of software when the hardware can't really scale out. Is that correct? Okay.
Yeah. So I mentioned reassigning servers. You can actually reassign hard drives. Hadoop actually doesn't care much where a hard drive is connected. So we can take away a server and take the hard drives that were connected to it and put it on different servers, and Hadoop picks up, and the data is still there. So you can shrink a cluster very easily. You can grow a cluster. And over time, we'll add some copy services so we can really move data if you want to do that kind of thing.
The smallest unit of allocation in this is a single drive.
Is a single drive. So our box, this is our box. So it's a 1U chassis, 4 independent adapter cards. Each card does 20 gigabits of throughput, translation from Ethernet to SAS. And it's dumb as a rock, and we're proud of that. So we don't do RAID, we don't do volumes, we don't do LUNs. It's a data path. On the other hand, we do have very good management probes into the JBOD, so we have a complete understanding of the SAS topology. We have different drivers for different JBODs to handle the different management firmware in each one. And we expose all that stuff up in the GUI. Satya will talk a lot more about this in his presentation. The other thing is the management is based on Redfish. I don't know if you guys have heard of Redfish. It's a new standard meant to replace IPMI as kind of a box management protocol. And it's actually catching on in lots of different areas. We have a management Ethernet port per blade here, but you only have to connect one in the box to get connectivity to all of them. But you can connect as many as you like.
So can you have, in terms of the storage across that cluster, just to the previous slide, you have like different types of drives spread across your cluster and take advantage of there. Is there any kind of like auto scaling and those? Oh, sorry, no, auto tiering, that kind of thing?
No, not at our level. Again, Hadoop has some tiering capabilities these days, and so that kind of thing, again, we view as a software problem.
Right. Okay.
So whatever software on top, we'll still see the different types of drives.
Right.
We're not virtualizing anything about the hardware, except the connectivity. Demo time, it's early. So good time for more questions on the software framework if you have any. Or
Are you going to get into like the reduction of cost in this model compared to a traditional model?
not a lot. If you look here, there's several ways it reduces cost. First, you have a broader choice of server FRUs, right? So a 1U server versus a 2U server with the identical components is cheaper, just because it's higher volume. You don't need as many servers if you have a colder application, right? So
you could have 8 quarter U servers in a 2U box instead of just one.
Yeah. So
there's a lot of rack space savings.
Yeah. So we can do a lot for density, and but pure cost is not the driving factor here. It's more about the flexibility.
What we've calculated is, and the way we price the product, is you save enough money, just enough money, to pay for us. So you get all the flexibility and responsiveness, and it doesn't cost you anything more. And then when you go through one processor upgrade cycle, then you've saved a whole bunch of extra money.
Are you just paying for the hardware then?
So by the savings of buying these things diskless and in JBODs, and with the rack space savings as well added in, the cost of this type of deployment versus the traditional type of deployment should be about the same. I'm sorry, I lost your question.
So he was talking about.
Yeah, like how are you licensing it, like based on capacity, or is it just you buy this and then I can throw as much
so you buy the box as a box. It's very low cost, $6K for this box, list price. And then the software is where the real value is, and it's per node per year and per disk drive per year.
It's not based upon storage capacity. It's based upon drives. Spindles, yeah.
So basically, it's based on the number of disaggregated components, right?
Because that's what we are managing, so that's what we charge for.
Mm-hmm.
So how do you control things like HCLs for, because there's a pretty broad range of hardware providers out there. You guys have an HCL, some stuff that you've already QA'd and approved. Like, how do you approach that?
We have an HCL for the JBODs. For general servers, it's kind of not our problem because we come in after the server has been installed with Linux. We install our stuff on it, and if it doesn't work, there's something terribly wrong with the server. Similarly, for switches, we're not requiring anything fancy out of the switch. So if you can't switch TCP/IP Ethernet, something is horribly wrong.
Actually, for the servers, our interface point is Ethernet ports.
Yeah, and we are putting together reference architectures with each of the big server vendors. So we have a reference architecture for Dell right now. We're working on one for Cisco and HPE and Supermicro. So, but basically we run such standard, mature interfaces that everything should just play together.
I should mention, you don't have to have 10 gig in the servers. You need to have 10 gig or better. So 25 gig is entirely viable today. Our box only does 10 gig, but 25 gig will downshift to 10 gig. So you can do 25, 50, or 100 gig in the server. One of the things we enable is using much fatter servers. If you look at things like Spark, they want to cache, Spark wants to cache stuff in memory. Having a lot of little servers, each caching stuff, is far less effective than having a few servers with much larger caches. So we're trying to do the analysis and experimentation of, does a 4-node processor with, 6 terabytes of memory make sense for a Spark type environment? And that class of processor might need 100 hard drives talking to it. So that's something we can do.
It's iSCSI between the server and your adapter, though?
That's right.
Are you requiring QoS or anything like that?
Nope. We do load balancing. If you're really paranoid, you can set it up to have a dedicated network just for our traffic, but that's not necessary.
Using jumbo frames or?
We do require jumbo frames. And we also require LLDP to figure out exactly who's connected where.
Okay.